we said that something like a combustion of carbon, for example, with to give you carbon dioxide, okay, that involves two elemental substances, so that's uh, a redox reaction, right? But how can there be electron transfer there? Carbon dioxide doesn't, it's not an ionic compound. Here's your Lewis structure for carbon dioxide. The carbon and the oxygen are sharing electrons. There is no electron transfer, it seems, right? But you have to realize that, okay, even though the carbon and the oxygen are sharing atoms, in general, sharing of atoms is, I mean, sharing electrons, in general, sharing of electrons is not equal. We've learned earlier that this is a polar bond. This bond is polarized towards oxygen. Electrons actually spend more time with the oxygen than they do with the carbon. Similarly, this bond right here, carbon to oxygen, is also polarized. So we also say that this bond right here is polarized towards oxygen, okay? So in a way, even though the electrons are shared, there is some partial transfer of electrons to the oxygen from the carbon. Okay, so in that sense, we say that you can think of oxygen atoms as having gained electrons and the carbon as having lost electrons in the process of burning carbon to give you carbon dioxide. Okay, so that's why that reaction is also considered a redox reaction. Now, we don't like to have to deal with partial charges, okay? And so, as a matter of convenience, we define the thing called oxidation number, okay? To allow us to determine if a reaction is a redox reaction, okay? Without having to worry about partial charges. And in general, what we do is we examine our reaction and we look at the oxidation numbers, and if we see that a particular atom has gained oxidation, has an increase in oxidation number, then we say it's oxidized. And when you see a decrease in oxidation number, then it must be reduced. Okay? So this one, increase in oxidation number is oxidation, decrease in oxidation number is reduction. Okay, so what's an oxidation number then? Well, if you're dealing with a single atom or a monatomic ion, a monatomic species, the atomic number and the oxidation number is just the charge. So for example, what would be the oxidation number of a magnesium atom? What's the charge of a magnesium atom? It's neutral, so the charge is 0. So oxidation number of a magnesium atom is its charge. What's the oxidation number of chlorine in magnesium chloride? Well, what do you know about magnesium chloride? It's made up of magnesium ions and chloride ions, right? For every magnesium ions, you see 2 chloride ions. So given that, what's the oxidation number of chlorine in magnesium chloride? Each chlorine atom in MgCl2 is actually in what form? In the form of chloride, right? So the oxidation number of Cl, or chlorine, in MgCl2 is -1. Okay, there's 2 of them, but each chlorine has a charge of -1. So each chlorine in magnesium chloride has an oxidation number of -1. What's the oxidation number of magnesium in MgCl2? +2. Yes, the total is 0. The total is 0 because you have a +2 and 2 -1s. That's a total of 0. Okay? Now, so that's if you're dealing with monatomic species. Okay? And you have to realize that you can have a monatomic ion within a compound. Right. Now, what if you have a molecule or a polyatomic ion? Then the atoms there do not have a charge. Okay? A charge, the whole thing, the molecule has a charge of 0. A polyatomic ion has an overall charge. But the individual atoms within that structure do not have a charge. Okay? So in order for us to be able to keep track of electrons, we have defined the oxidation number as a fictitious charge that we assign to an atom. So this is similar to what you've learned when you talk about molecular structure, when we were dealing with molecular structure. This is similar to what we call the formal charge. Except in the formal charge, when determining formal charges, we assign equal ownership to the shared electrons to the atoms that are sharing them. Okay? But when you're determining oxidation numbers, you assign ownership of the shared electrons to the more electronegative atom. So let's illustrate that with carbon dioxide. Okay? If you were to draw carbon dioxide, the Lewis structure looks like this. All right? So, if you recall, how many valence electrons does an oxygen atom have if it were by itself? Where would you find oxygen in your periodic table? Oops. Where would you find it in your periodic table, huh? Group 6, right? Group 6A, column 16. Okay? So that means it will have a neutral oxygen atom, if you recall, as an electron configuration of 1s2, 2s2, 2p4, right? It has 6 valence electrons. Okay? By itself, if it were alone, an oxygen atom would have 6 valence electrons. Now, in this structure, okay, remember a Lewis structure shows you how the valence electrons are distributed among the atoms. In this structure, the oxygen owns how many? 2 plus 2 plus 2 plus 2. It's surrounded by an octet, right? So it appears to own 8. Okay? We say it appears to own 8 because we're going to make the assumption, for purposes of calculating oxidation number, you assign ownership of shared electrons to the more electronegative atom. So we're going to say that even though this double bond right here is shared between carbon and oxygen, it actually, we're going to assign ownership of that to oxygen. So we're going to say it belongs to oxygen. So from 6 in a neutral atom to 8 in the structure as drawn here, it appears to have gained 2 electrons. So we say it has an oxidation number of -2. So in this structure, in carbon dioxide, this oxygen atom appears to have gained 2 electrons for purposes of calculating oxidation number. And this oxygen atom right here also appears to have gained 2 electrons, so its oxidation number is -2. So we are assigning a fictitious charge to it. It's not really -2, the actual charge, right? But we don't have to worry about partial charges. So we're just going to say, oh, let's just give him the whole thing just for counting purposes. Okay, and then carbon right here, we say, appears to have lost how much? 4. Okay, carbon, if you look at your periodic table, is in group 4A, right? The column number where your atom belongs tells you, this is a review, tells you how many valence electrons a neutral atom would have. The Lewis symbol for carbon atom would have 4 dots, remember? Oxygen would have 6 dots. Okay, 2s2, 2p4 would give you 6 electrons. Okay, so in carbon dioxide we say, okay, that the oxidation state of oxygen, each of the oxygen atoms has an oxidation state of -2. They don't have a charge of -2. Their oxidation state is -2, or their oxidation number is -2. Carbon, we say, has an oxidation number of +4. That +4, that's not the charge of carbon. That's a fictitious charge we're assigning to carbon for purposes of keeping track of electrons. So that's called the oxidation state of carbon. Okay? What about peroxide? Another example here. What's the Lewis structure for peroxide? You have a single bond between the 2 oxygen, and then you have how many valence electrons do we need to distribute for that? Each oxygen has how many valence electrons? It belongs to group 6A. It has 6 valence electrons times 2, that gives you 12, right? And then you have a -2 charge, that means 2 more electrons, as a total of 14 electrons. And so the way you draw the Lewis structure, this is valence electrons, okay? You draw the Lewis structure for peroxide. You draw a single bond, do an octet around each oxygen, and that takes care of 14 valence electrons. There's 6 here, 6 here, 6 lone pairs on each oxygen, and there's 2 in the single bond between them. That's a total of 14. So the Lewis structure for peroxide is O2 with a -2 charge. So I put this in brackets and put a -2 on the outside. Okay, so that's the Lewis structure for peroxide. So based on this Lewis structure, what is the oxidation number of oxygen? Well, which one's more electronegative, oxygen or oxygen? Neither one, right? So we cannot assign ownership of these 2 electrons in between to either one, right? They have to be split 50-50. So if they split 50-50, how many electrons does this oxygen appear to own? 7. And how many does this appear to own? 7 valence electrons. Normally an oxygen atom would have how many? So this one appears to have gained 1, right? So 7 minus 6 minus 7 would be -1. So we say the oxidation number of this oxygen is -1. The oxidation number of this other oxygen is also -1. It's as if each oxygen gained 1 electron. So we say the oxidation number is -1. They don't have a charge of -1. The pair as a whole has a charge of -2. Okay? But it's as if each one has a charge of -1. Okay, what do you think the oxidation number of mercury is going to be in Hg2 plus 2? That's the mercury 1 ion. Let's make that a clicker question. Is it 1 or B is it 2? Plus 1 or plus 2? For each mercury in the mercury 1 ion, or mercurous, this is called mercurous ion, or mercury Roman numeral 1. What is the oxidation number of mercury? Is it plus 1 or plus 2? Is plus 1. Okay? The pair as a whole, okay, they're sharing electrons. The pair as a whole has a charge of plus 2. Since we can't expect either one of them to own the shared electrons, we have to split electrons 50-50. We expect both of them to have the same oxidation number, right? So since the overall charge is plus 2, it's as if each one has a charge of plus 1. So we say the oxidation state is plus 1. They don't have a charge of plus 1. They have an oxidation state or oxidation number of plus 1. And that's why, that's really what that numeral, Roman numeral means. It's not really the charge. When you attach it to the name for a transition metal, that's actually oxidation number. So when I say mercury 2, okay, Roman numeral 2, we said that that's mercury with a plus 2. Okay, that 2, in this particular case, just happens to be this. It just happens to be that plus 2 is also the charge and the oxidation number. Okay, but that Roman numeral 2 actually refers to the oxidation number. Okay, so in fact, sometimes you would write for something like maybe SO2, for example. Okay, the oxidation number of sulfur here is plus 4. Okay, we'll learn how to do that in a short while. And sometimes you call this sulfur Roman numeral 4 oxide. Okay, that's one way it could be called. Okay, you probably learned earlier that what do you call this? Sulfur dioxide, right? So this is another way that could actually be called. You specify. So when you say Roman numeral 4 there, you're specifying the oxidation number. Sulfur certainly doesn't have a charge of plus 4 here. Okay, its oxidation number is plus 4.